I'm Mohammed Orangian. Today we are going to practice a tutorial about combustion. The tutorial 1, a gas fuel has a volumetric analysis, CO 9%, CH4 32%, H2 44%, O2 4%, N2 11%, and is completely burned using 20% excess air. Calculate the stoichiometric air per meter cube of fuel. To proceed with the solution for this tutorial, first of all, we need to just write down the combustion equation. So for combustion equation, for any combustion equation, on the left hand side, we have got the fuel elements. Over here, the fuel elements are CO plus CH4 plus H2 plus O2 plus N2. So these are the fuel elements. And for combustion, we need the presence of oxygen and basically the presence of the air in the atmosphere. So we consider the elements of air, that means oxygen and nitrogen. This is the left-hand side of the combustion equation. So now we just consider that we have got 100 moles of the fuel. So the first consideration is 100 moles of fuel. So if it is 100 moles of the fuel, so we are going to have 9 moles of CO and then 32 moles of CH4 and 44 moles of H2 and 4 moles of O2, 11 moles of N2. But for oxygen, we consider a coefficient of A as the stoichiometric moles of oxygen. So then we put A here, and then the ratio of nitrogen, it is of the ratio of 79 divided by 21 times A. So this is the coefficient of nitrogen. But the point is that we have got 20% excess air. So then we should have 1.2 in the bracket, the elements of the air. So this is left-hand side of the combustion equation. So on the right-hand side, we have got combustion products. So combustion products, we know that for the combustion of carbon, complete combustion of carbon, we are going to have CO2. Plus, we have got excess air, so definitely we are going to have O2 in the exhaust product. Then we are going to have nitrogen in the exhaust product, and H2O as a result of complete combustion of hydrogen, H2O. We don't know the coefficient of the combustion product. So we will put the unknown coefficient of B, D, E, and F. So this is our combustion equation. So now we will start the equation balance. So we go for equation balance. So that means based on the conservation of the mass flow, we need to have the same amount of every element in the left hand side and on the right hand side. So we start with the carbon. So in equation balance we will consider carbon, and that is C. On the left hand side the coefficient of carbon is B, and on the right hand side we have got 9 plus 32, and that's it. And this is equal to 41. So B is equal to 41 moles of carbon per 100 moles of fuel. So next one, we consider the hydrogen. So we consider hydrogen, H2. So the element of the hydrogen on the right hand side is F. So on the left hand side we have got 32 times 2, and then we have got plus 44, and that's it. So F is equal to 108 moles of hydrogen per 100 moles of fuel. 100 moles of fuel. So we consider the next element, which is nitrogen. So the next element is nitrogen, N2, and the coefficient of N2 on the right hand side of the equation is E, and on the left hand side we have got 11 plus 1.2 times A times 79 by 21. So we get this equation. So the next element is going to be oxygen, which is O2. And on the right hand side of the equation we have got B plus D plus 0.5 F. This is all the coefficients we have got on the left hand side. On the right hand side for oxygen we have got 9 times 0.5 plus 4 plus 1.2 A. So this is the equation that we need to solve the equation and get the unknown coefficients. D is the amount of, for the excess oxygen, so D is going to be 0.2 A. This is the amount of excess oxygen. So now we put the values in the equation. So B is equal to, from this equation, we have got B is equal to 41 plus D is equal to 0.2A and 0.F, F is equal to 108, and on the other side we have got 4.5 plus 4 plus 1.2A. So 1.2A and 0.2A, we just shift it to the right side of the equation. So from this we get A is equal to 86.5 moles. So this is A. And having A, we can get D. D is equal to 0.2A, which is 0.2 times 86.5. So this D is going to be 17.3 moles. And then we have got, from this equation, we put the values and we get E. E is equal to 11 plus 1.2 times 86.5 times 79 by 21. So from here we get A is equal to E so we get E equal to 401.48 moles. So we got all the unknown coefficients in our combustion equation. So now we just write down the complete combustion equation. That means 9CO plus 32CH4 plus 44H2 and then plus 4O2 plus 11N2 plus 103.8 O2 plus 103 plus 390.5 N2. So this is the left hand side of the equation. On the right hand side we are going to have 41 CO2 plus 17.3 O2 plus 401.5 N2 plus 108 H2O. Now part A of the question, asking about the stoichiometric air, which from our combustion equation, that is equal to A times O2 plus A 79 by 21 and 2. That is for stoichiometric air. So we put the values for that. So A is equal to 86.5 plus 86.5 times 79.21. So this is equal to 411.9 moles per 100 moles of fuel. But the question is asking about the stoichiometric air as volume. So we need to do a kind of conversion. So stoichiometric air is going to be equal to, divided by 100, we are going to have 4.12 meter cube of the air per 1 meter cube of the fuel. We know that the ratio of volume is the same as the ratio of the moles, so this is part A. Now part B of the question is asking the dry exhaust analysis. Dry exhaust analysis. And it is volumetric. So what we need to do is just make a table, and in the first column we are going to have the dry product, which is CO2, and then we are going to have O2, and we are going to have N2, and then the total. So CO2 per moles is 41, O2 is 17.3, and N2 is 401.48. So these are our products as a result of the combustion. So total is going to be 459.8. Now we can calculate it as a percentage. That means 459.8 as the total we consider as 100%. Then for each element, that means 41 divided by 459.8, we are going to have 8.92%. The same way for the oxygen is going to be 3.76%, and for nitrogen it's going to be 87.32%. So this is based on percentage. So this is dry exhaust analysis. So now the solution is complete. Thank you.